In this video, we're going to look at graphs. Okay. First, we're going to look at an ordered pair. What is an ordered pair? We're going to start with the basics here. An ordered pair is a set of points that go together, of numbers, we'll say. Typically, you see this in the form x, comma, y, with parentheses around them as standard if you have two variables. If you had three variables, you would have x, comma, y, comma, z, and so on. So let's look at equations and then what is a solution, and we're going to look at this from sort of a point of view by looking at equations as graphs of points. So a solution of some sort of equation, an equation first off is something like this that relates two or more variables, x and y, and a solution is an ordered pair that makes the equation true. Or you could say that satisfies the equation. So for example, is negative 2 comma 1 a solution to the equation y equals x squared minus 3? Well, you can tell by plugging it in, and these you assume go in order, so you would assume that x is negative 2 and y is 1. So we're going to plug that in and see if it's true. So if I plug in 1 for y, I will have 1, and this is really a question, does that equal to x squared minus 3? If x is negative 2, that means negative 2 squared minus 3. Those parentheses right there are very important because negative 2 times itself, when we square it, negative 2 is actually positive 4, which is different than the negative of 2 squared, which I'll write in a moment. So 1 does equal 4 minus 3. So yes, that one is a solution, we would say, because it made the equation true. What about 2 comma negative 1? So let's try that one. If I plug that into the equation, y equals x squared minus 3. Y is 2, so we're asking, does 2 equal, I don't know, does it equal, oops, no, I wrote that backwards. Y is negative 1. Does negative 1 equal x squared minus 3? So x is 2, 2 squared minus 3. Well, 2 squared minus 3 is equal to 4 minus 3, which is 1, which is not equal to negative 1. So no, the point 2 comma negative 1 is not a solution because it does not make the equation true. Okay, typically your independent variable is x. Okay, it's the input to an equation, and the dependent variable is typically considered y. It's the output that you get when you choose a particular x. So you could choose a y and then see what value of x or what values of x make that particular y work on an equation. Or the more common way is to choose x and then see what y is. Okay, so x is the independent variable, that's the thing you choose to plug in, and y depends on x. Okay, how to graph equations? Well, there's all kinds of studies on that. We could go really in depth here, but we're just going to look at simply how to graph an equation by plotting points. Well, a graph, what is a graph? First off, it is a visual representation of all of the solutions. So all of these solutions to a particular equation. Okay, because most equations have infinitely many solutions. You know, when x is 1, y could be one thing. When x is 2, y might be something else. there's infinitely many solutions. We can't list them all out. So instead, we often visualize the infinitely many solutions to an equation by graphing it. So how do you graph? Well, you choose the independent variable x, and then you compute the corresponding y values to see what goes with them. Now the x-axis is this one right here. This is x. And the y-axis is typically your vertical axis here. So it's common to make what they call a t-chart, like this, like a big T. We're going to choose some different x's and compute the corresponding y's. And don't forget the negative values of x as well. And since I would like to go in order, I'm actually going to start with a few negative values. Let's try -4 and maybe -2, 0, 2, and 4. And that's just a guess. I'm guessing that will be enough points to get an accurate picture here and figure out what's going on. So if we plug in -4 up here, I'll write it out on this one. We'll have 1/2 times -4 minus 9. This is the same as -4 divided by 2. Okay, or 1/2 of -4 is -2. Minus 9 is -11. If I go by ones, if each tick mark is 1 here, that's off the graph. So let's try -2. Plug in -2. 1/2 times -2 is -1. Minus 9 is -10. I'm still off the graph there. Let's jump up, and it looks like I'm going by ones here. So let's jump up to 0. My guess is it's going to be -9. Yeah, 1/2 times 0 minus 9 is -9. Let's see, 1, 2, 3, 4, 5, 6. So one thing we could do is make the y-axis go by 2. I think we'll do that here. Or 3s or 4s or whatever you want. If you're going to change the scale of the axis, though, you need to label it. Let's make this go by 2, 4, 6, 8, and so on. -2, -4, -6, and so on. So when x is -4, we're going to go by 1s on the x-axis. Keep going here. And you don't have to label every single one. You just need to label enough to get the pattern for what each tick mark represents here. +4. Okay, when x is -4, y is -11, so we go out on the x-axis here to -4 and then down to -11 and plot that point. Then when x is -2, y is -10. X is 0, y is -9. You can see this is increasing very slowly. Just a few more. When x is 2, 1/2 times 2 is 1, minus 9 is -8. 1/2 times 4 is 2, minus 9 is -7. So we have 0, -9, 2, -8. Oops, all right, 2, -8, and 4, -7. So the graph of that line would look something like that. Next, we're going to look at graph on your calculator. Now, many of you probably have something like this, a TI-84. To graph a function or an equation, you go to y equals right here, and then you can type in an equation. So let's just type, for example, actually let's just do the one that we just graphed. 1 divided by 2 times x. I didn't actually need the times sign there, but put it for clarity. Okay, minus 9, and let's hit this graph button over here to see what the graph of that equation looks like. And there you can see it looks just like the one that we just graphed. To change your window, you can go here, and that can change the x values that are showing, which are these x values, and that's the min and the max, and the y values. This means what are the tick marks. The tick marks go every 1 currently. You can also go to, let's see, zoom right here to just zoom in or out from where you're at. Another useful item is the table. It's above graph. So if you go second table, okay, it'll actually tell you different y values for the different x's. And one thing you can do is go to table set above windows, a second table set, and you can tell it where you want to start, what you want it to go by, so 1s, 2s, whatever. You can also, and this will be useful later in this course, you can also change this to ask. Okay, hit enter, and you can go back to table, and then you can enter any particular x value that you want, okay, and it will tell you the corresponding y value. So that's it for the calculator for now. If you need more help, just let me know. And next, let's look at this example for interpreting graphs, okay? This is a very straightforward example. We're looking at how to read information off of the graph. So in this example, the deer population of California from years 1800 to 2000 is approximated by this graph below. We're just going to approximate here. The term abundant refers to populations above 700,000. Common refers to populations between 400,000 and 700,000, and scarce refers to populations below 400,000. Okay. So for which years were deer common? In other words, when was the population, for which years means when, okay, when, which means in this case we're looking at the x value. So what you want to do is identify, are we looking for an x value or a y value? In this problem, the years are represented by x. So in what years is the population between roughly 400,000 and 700,000? So let's draw some lines in at 400,000 and at 700,000. That's a rough estimate there. Okay. And let's see, so it looks like most of the time the deer population is within this range. So from year 1800, at least, it starts out in this common population zone. Let's see, it's in that zone until right about there. Okay, let's see, let's estimate. This is 1850, that's 1900, that's maybe around 1860, I'm just guessing here. And then it pops back up, so maybe I'm going to estimate 1865 or something. And it stays above 400,000 again until right there. That's maybe 1890. Then it comes back into, or goes below it just briefly, and it comes back into the common range right about there. I think that's crossing right at the year 1900. And then it stays in the common zone until there. Maybe around 1930 or so. And then it dips back into this, let's just estimate that it's common in that whole interval. So right about there, around 1970 to 2000. We don't really know what happened after 2000 from this graph. Okay, in what years, for what years were deer abundant? So that is asking for what years is the population above this 700,000, and it looks like only really briefly from here to there. So that's roughly years, I think I estimated that, let's see, as 1930 right there. So from about 1930 to right about there, which is about 1970 or so. And when were they scarce? That's beneath 400,000. So right there, just a tiny bit, and right there, just a tiny bit. That's these two gaps. So from about 1860 to 1865, and let's see, right in there, maybe around 1890 to 1900, and my estimates may be off, but that's close enough. And in what year was the California deer population at its highest? So that's asking when is the Y value the largest. Okay, and it looks like it hits its peak right about there. I'm going to estimate that to be maybe 1960. And then approximately what year was the California deer population the lowest? It's tough to tell from looking at if it was there or there. I've kind of written on this graph. I think probably at that point. So let's estimate around 1865 or so. Right? It looks like in 65 it jumped straight up. Okay, you can always put that symbol, it means approximately, or you can put that sort of like an equal sign, but approximately. Here I would just recommend one like a squiggly sign. One squiggly, approximately 1865.